Hi guys, can you hear me? Oh, you have done school
Yeah.
today? Excellent. Justin, you're at home.
Yeah, we've
Yeah,
like
we have the
a
day off today.
special day off.
How come middle of the day? Oh, is it because it's my birthday or what?
No, our headmaster gets to declare like one day a school holiday every year. So he did that this week.
Okay, I thought you're celebrating the Earth Day.
Nope.
Uh, we still are missing Tyler and Griffin.
I think Griffin's here.
Where is Griffin? Hiding, hiding, hiding. Where?
He just sat down.
Hello?
Oh yeah, okay.
Oh, hi. Sorry, we had problems last time with our system, so I couldn't get on.
But were you able to watch the recordings at
I
least?
I emailed my person who's supposed to contact Mrs. Obey, I guess, and she said she's getting the lectures for me. So
Okay.
I'll have them.
So, yeah, because we did quite a few things. It's not difficult, but again, like needs a little bit of help to go through it. Other than that, this is one of the easier topics. The next two topics are fairly straightforward, and then we'll stop with that. Because the exam is supposed to be 2 weeks from today,
Yeah.
right? So that means you don't want to try the final exam like the way you did the midterm exam.
So a question about that. Would it be possible to maybe take the mid or the final exam later? Because 2 weeks from now is right in the middle of APs.
Yeah, that's okay with me.
Okay.
I mean, because I don't know why they put the exam date as the 5th. I thought some schools were closing early, but I mean, it's okay with me if you want to take it after the AP exam. Right? I mean,
Awesome.
all I have to find out is when the grades are due, but usually that has not been a problem because the grades are due. I don't know, but I'm guessing it's more like end of the month.
All right.
So that means we won't be having class 2 weeks from today? Or is that going to be our last class?
2 weeks from today is the last class.
Is the last class, okay.
I mean, actually, they said it was the exam, so it's like 3 days from today, or the Monday is the last day. But since we are not going to have the exam, we could still continue to have that also as the last day, the Friday. Oh, sorry, the Wednesday.
Okay.
All right.
And after that, if you experience any withdrawal syndromes, you can watch the recordings. Do you remember what we were up to? Can you see the screen?
Yeah, I can see it.
Yeah.
Something that helps here, since all of us are sitting with your computers. Are you all sitting with a computer in front?
Yeah.
Yeah.
Okay. So one of the things that the way I would like to do is like have a chat that's continuous. So if you have questions, it takes a little bit of effort. If you think the microphone is a problem to turn on and turn off, you can chat. Right? So you can write questions right away. And that's how the other classes usually go, is that they're continuously chatting. And the good thing about chatting is all five can chat at the same time, and still it won't be interrupting the others. So if I ask a question, then all of you can answer at the same time. So what were we trying last time?
We were going over the two different approaches to finding a minimum spanning tree.
Yes, right? So a minimum spanning tree is a tree, like if you have a graph or if you have edges, a graph, what we're trying to find out is identify the links that will allow you to traverse connect all the vertices, right? All the links that are, and what we were trying, that is spanning tree. A spanning tree is something that traverses all the vertices, and what we were trying to do was come up with what's called the minimum spanning tree without creating cycles. So what are the minimum the edges we need to select so that the cost is minimum? Right? The cost is minimum is what we were trying to do. So how did we go about doing it?
We were using cuts.
We're using, yes, at least the property we were able to at least agree on is the fact that we define what's called a cut. Cut is something. The first thing, so this is so that Griff kind of has some understanding of what we did last time. So we were trying to create trees. This time the trees graph had cost in it associated with it. Right? So there's an extra number on the edge that's called the cost of the edge. So previously, the first two chapters, 4.1, 4.2, we did not add cost to it. They were just like links. We were not associated, we're not looking at cost. And so the first thing was, okay, if you have a cost, can we use the same representation we used before? So we created a class called edge, and we added the cost to it as an extra field. We added a cost as an extra field. It's called the weight. Right? Other than that, it has an A node and a B node, or the two nodes, two ends, and then a cost. And then of course we have other methods, like if you say either, then it gives you it just gives you one end of the node, end of the edge. And if you say the other and provide the first one, it returns the other one. Few simple methods to be able to do that. And the compare to method will take two edges and return based on the weight of the edges, which one is a smaller one. So we have to make a slight modification to the class called edge. So because the cost is extra, that was an extra field. Of course, we could use the adjacency list representation for that. All we have to do is add the extra field, and the adjacency list representation we have used in the first two would also work here too. And so far we hadn't done anything different. And of course, the first algorithm we were trying to do was, how do we identify a minimum spanning tree? Right? So it's an edge-weighted graph, and so this is the entire class for an edge-weighted graph. The edge-weighted graph has an edge, a list of, right? Oops, where's my pen? It has a count of the number of vertices and an array of bags. An array of bags. Bags are the ones into which you are going to put the list, adjacency list. An array of bags, because we use a bag because we don't have to remove it. Hopefully the graph will remain as is. We won't be removing edges from it, because that was the missing part in the bag. So this is the constructor that if you specify the number of vertices, it sets the number of vertices to V, and then initializes the bag with a loop. So you have a set of empty bags attached to the array. And that's an empty bag because they're all new bags. Right? Create an array of new bags. And then this is, of course, if you're adding an edge, every time you add an edge, it just adds it in the appropriate array location. So that's all. That's a minimum modification we have to do, which is almost the same as what we did before. So there's nothing different this time. How can we represent a minimum spanning tree? We can represent the minimum spanning tree by a list of edges. Right? So you just collect the subset of the edges from the spanning tree, the entire graph. That's what a minimum spanning tree is. A minimum spanning tree will consist of a subset of the total number of edges. So there's nothing that we need to do extra. So one property we looked at was that what's called a cut property, meaning that a cut, what is a cut?
It's when you partition the graph so that it's split into two halves, neither of which can be empty.
Yeah, so you want to create a set of vertices, right? Cut it into two, create two sets, and then there's one set of vertices on one and the other set on the other side. A cut is the it partitions the thing into two non-empty sets, and a crossing edge is an edge that goes from one side, one cut to one set to the other set. So all the edges that cross the cut is called a crossing edge. So if you partition this into two and put all the vertices on one side and the other vertices on the other side, and then you have this crossing cut. Crossing edges are the edges that cross from one side to the other. So this would be one partition, one set, and that's the other set, and all the edges that cross from one side to the other is called a crossing edge. And what our spanning tree algorithm was based on one principle, that the span, if you when we create the spanning tree, the crossing edge with the minimum weight will be included in the minimum spanning tree. So there are many edges that are crossing edges. They go from one set to the other set. And what we agreed was that the crossing, the out of all these edges, the one that's going to be included in the minimum spanning tree is the one that has the minimum cost. Right? So we need to choose the one that's a minimum cost. And intuitively we said, yeah, if that's not the case, and if you choose another edge, then certainly we can replace the edge with the one with the minimum cost. If you choose any other edge that's not the minimum cost, then by definition it won't be the minimum cost, because we can still find another edge with the minimum cost. Therefore, the edge with the minimum cost will be in the spanning tree. And then we looked at two. So that's what the whole principle is all about. The whole thing is based on the property that if you take a cut, identify all the crossing edges, and choose the one that has the minimum cost. So once we agree on that, then there were two ways of. There were two different algorithms: Kruskal's algorithm, Kruskal's and Prim's algorithm. And the only difference between both, and let me pull out the slides for Greedy, Prim here. Start with Prim's algorithm. So the only difference between both was, so we, in Prim's algorithm, we are going to start with a crossing. So essentially what we are going to do is we're going to use the same principle of the crossing cut, and we are going to start with any vertex. A crossing cut that contains one vertex on one side and all the other vertices on the other side. Right? So you create a list of vertices and then create a crossing cut such that, in this case, let's say for example, we can put 0 on one side and all the other vertices on the other side. And identify all the vertices that's going out of 0. That means this, that, this, and this. Make a list of all the edges that's going out of that. So you have to create a little priority queue. Right? So you create a priority queue, and then so you have this vertex, pull out all the edges that's going out of it, create a priority queue, and push all of them into it. You know what a priority queue would do? When you remove from a queue, what would we get?
You always get the smallest or the least costly edge.
Yeah. So we don't have to traverse. It's an easier way to get. It's a priority. So we'll just remove the priority queue, and then we'll remove that stuff, right? So remove the priority. So let's choose the one, and then let's say, for example, if this happens to be, I don't know which one that happened to be. That happened to be, let's say, that one, 0 and 7. If this happens to be 0, 7, then move that into the crossing cut. Move this into one side and say now the set is going to be, your partition is going to be 0, 7 against everything else. Right? So initially, so a priority queue consists of, so we added all the vertices. So the priority queue consisted of all these edges. You choose the one with the minimum cost, because that's a cut, and we are going to choose the one with the minimum cost. Okay? And what once we discover the second thing, we have discovered 0, 7. So we make a list of the edge that needs to be added into the minimum spanning tree edge, and then we have discovered additional edges leading out of 7 now. Add them into the priority queue. Add those. So we have discovered a few more. So that one, this one, and this one. There are four new edges we have discovered. Add them into the heap, and you'll have a heap that looks like this, because the newly added ones are the 1 to 7, 5 to 7, 2 to 7, and 4 to 7. Add them into the heap, and then remove the one with the minimum cost. That would take 1 to 7. Give me 1 to 7. Right. So now I create a cut that consists of 0, 1, and 7, and all the others on the other side. So I will keep repeating the process. I'll keep repeating the process, and at this point, you have to go under what to do with the edges that are going to be duplicates, or for example, the ones I don't need. Like you may sooner or later you'll end up with, like if you're going to add and says now that I have added 1 to 7 and add the new set of edges. The question is, what about the edges I don't need? Are there some extra edges here? Because I'm adding the new ones, 1 to 3, 1 to 5, and 1 to 2. These are the newly discovered edges. Like you see that there are extra redundant edges in that list. Right? For example, 1 to 2 is right? Which ones, for example?
1 to 2 is redundant.
1 to 2 or 1 to 1 to 2 or 7 to 2. So we don't know which one is the redundant, right? Because whichever the smaller one needs to be maintained and the other one needs to be removed. Similarly, to go to 5, we have two ways of going to 5. 1 to 5, 7 to 5. And going to 4, you have 7 to 4 and 0 to 4. So we can implement two different versions of it. One version would be, at this point, remove the ones that you think are not needed. Like if you newly discover an edge that will make the cost minimum, then you can throw away the old one away. And that's called the eager version of it, of Prim's algorithm, where you're going to remove them. Remove those vertices, so the edges that are not needed, and keep only the ones that's needed before we. The lazy version is that now that we are going to take, when we remove when we don't remove it early, we just leave it in the heap. But before we include it, we need to verify whether that's a needed one, because we may have already connected that vertex. We just have to verify whether that's needed. We have to do that. So 0 to 2, do we need 0? Like, say, now the minimum cost is 0 to 2. So let's take that out and include 0 to 2 is needed. So now I have a set that consists of 0, 1, 2, and 7, and then everything else on the other side. Right? We missed losing one. We lost someone. Right? And then so we make a list of these edges again, and then we are going to have a list like this. These are the crossing edges. This consists of the crossing edges here. And these are the edges that have been added to the minimum spanning tree. Take the next smaller one. Before you add it, let's check whether 2 and 3 are in two different sets. If they're in the same set, we shouldn't add it, right? Because so we may have to use, how do we determine two vertices are in the same set? What would be the fast way to do that?
I mean, you could just search the list of edges.
We can search the list. You can create a set, right? A set of vertices that's been reached, that's on one side. Alternatively, we can use union find. That's much faster, because union find, that's what union find was trying to do, was you give two, right? So a find is that each thing had a component ID. A find would say whether they're in the same component or two different components. So we can use a union find type of algorithm to see whether two vertices are on the same set. So we need a heap and we need a union find. Right? So there are two things we need to implement this. We need to implement the minimum spanning tree, because when you have thousands or millions of nodes, we cannot keep searching through them. When you're trying to process graph processing and other type of algorithms, when the nodes happen to be millions of nodes, we need to find a better way of doing it. So we can use a union find and a heap and do this. So then we discover 0, 7, and then add the newly added edges to that. Right? So now this is the minimum spanning tree, and then the crossing edges are the next set of edges. These are the crossing edges now. Right? So the crossing edges, and now we say, okay, what's the next minimum one? 5 to 7. So let's add 5 to 7 into the list of edges, and then we create a list of minimum spanning tree edges like that. The next one is 4 to 5, and we keep doing that. 4 to 5, we added into the minimum spanning tree, we have a 4 to 5. So as we remove, right? For example, 6 to 2, so as we actually throwing away the ones. Once 4 to 5 is discovered, we are actually, before we add, we need to verify whether the next ones are needed. Do we need 4 to 7? No, we don't need. So 0 to 4. So we'll keep. So as we remove, we need to check whether the edge is going to connect vertices already connected. If it is, throw it away and take a new one. And how long should I continue to do this?
Until the union find tells us that all the vertices are in the same component.
Yes, right? Or the number of vertices connected becomes n. Like if I know that the number of vertices are now n, I know that all of them having connected, I don't have to go through the rest of the list and throw them away. If I keep count of the number of vertices that's been connected, that's what Prim's algorithm was. So it's still based on the property of cuts. A slightly different versions. Any questions on this? Actually, what I'll do, okay, before we. So, questions on Prim's algorithm?
No, that's good.
So let's go and see how it's implemented. I don't know which page it is, but what is this one? That's Kruskal's. The Prim's algorithm, to summarize how that start with 0 and greedily grow. When you say a greedy algorithm is the one that selects it identifies what it wants quickly. Select the one that's shortest. I'm not going to just greedily grow the algorithm. The greedy algorithms select the ones, they greedily grab onto the next shortest one. That's a greedy algorithm. And then at each step, add t, add that, right? Add to t the minimum weight with exactly 1 point in that tree. That's which is take one of the crossing cuts, and that's what the greedy, right? And we can see that works. Prim's algorithm is a special case of a minimum spanning tree greedy algorithm. And so no crossing edge has a lower weight. So therefore we add that. Because we're looking at all the crossing edges. We maintain in the heap, we maintain a list of all the crossing edges, and we're choosing the one with the minimum weight. So certainly that works. So let's look at the code to do that. The code works like this. So what do we know? So we need to create a Boolean, an array of, this is to say whether it's already all the vertices, that's, have we included all the vertices into this, right? So we create a minimum spanning tree vertices. So we need to create a queue of edges that's going to be included in the minimum spanning tree, and we need a, no, this is to say whether they are in the, whether it's the same cut, right? Whether it's included in the minimum spanning tree. This is what I'm going to use for the union find. Right, union find, because I'm going to do a union find to say whether when I take an edge, I want to verify whether that edge needs to be added. So I'm going to create a Boolean matrix, a Boolean array, and then every time I add, I make it true, so that I don't have to add that again. Okay? So I create an array. Every time I add something, I mark them true, so that if both ends of the edge has been marked true, then I don't include it. Right? I need a priority. This is the heap, a priority queue, right? My sink and swim operations. So my constructor, all it does is it keeps adding the priority queue, initializes the priority queue, and it initializes the edges that's going to be included in the create a queue of edges, all empty initially, initialize an array of vertices marked false, and then start visiting the vertices. Let's start with any arbitrary node. It doesn't matter which one we just say visit that vertex. Visit that vertex means process it. Right? So what does visit do? What visit does is it creates the things what we were we were discussing. It marks the vertex as true. So that means that vertex has been marked. It's been visited. Plus, it goes through all the edges that's connected to it. Make a list. Add all the vertices. Go through all the edges that's connected to that given vertex. Add it into the. If the other edge, this is an eager version of it, meaning if the other edge has not been marked, if the other end has not been marked, that means it's already not included in the. Actually, this is lazy implementation because I'm not removing things. So I'm not going to add to that list the unwanted edges. So if you're going to, let's say for example, as we are growing the spanning tree, let's say this one has grows like this, and then let's say your spanning tree consists of something like this. Already identified a spanning tree. And into this heap, we don't want to add the new edge that's like this because we don't need that edge. Because we have already included in the spanning tree, so therefore we don't need that. Right? So we'll mark that. And see if the other edge has not been marked, if the other vertex has not been marked, go through all the edges that's coming out of this newly discovered vertex and look at the other vertex. The other vertex is false, then add that into the heap. That's my list of edges I saw before. Add that into the heap. And add that into the heap. So that's what visit does. What visit does is it marks that vertex as true. That means I have included that in my minimum spanning tree. And then go through all the edges leaving that's incident into that. And select the edges that's needed and add it into the heap and throw away the rest of them. So you repeat that. So that the initial step would be you have to start somewhere. So you start by starting at vertex 0, and then we do that. Now, this is it. Now what we do is, while the priority queue is not empty, now we are going to start removing one edge from the priority queue. Delete the minimum. Delete the minimum, that means give me the edge that with the minimum cost. And check to see, is that a needed edge? Because is that in the set that's already been visited? So look at both sides of the vertex to see is U and W are in the cut that includes the minimum spanning tree. If it is, go back and do the next iteration. If it is not, add that newly discovered edge into the minimum spanning tree. And then if the vertex has not been marked, visit that vertex. Which means add additional, discover and add into this heap the newly discovered edges. Right? So this is what Prim's algorithm is. It's exactly what we discovered. We start with we need to create three things. One for the vertices that's been marked so I said we were trying to create two sets. One set of vertices, a crossing cut with a set A and a set B. The set A is the one that's true, and the set A is the one that's false. Right? All the vertices which have been marked true are in the one set, and all the vertices which are marked false are in the other set. Initially, all the vertices are on the other set. Let's pick one vertex, mark it true, and visit that. That means identify all the edges that's going out of it. Select the ones that we want, add it into the heap. Then repeat the process while the heap is not empty. Delete the minimum. Remove the one that's right. Remove the edge with the minimum cost here. Find out what the vertices that's connected to that edge, because we want to know what are, because we're just removing an edge, so therefore I want to know what are the two vertices to this edge, and check to see whether it's on the MS minimum spanning tree or the false tree. If both are in the minimum spanning tree, throw this away. If one of the edges in the false tree, that means that edge has not been included. We enqueue the newly discovered the edge, and then visit the whichever one which has not been visited, visit that vertex. Right. So, any questions on this?
This doesn't have the feature where it like checks if you've already been to every vertex, right?
So this one, instead of testing it, that's what the Boolean is supposed to do.
Okay.
Right? So the Boolean would make sure that you're not adding anything that's unwanted. Before we add,
Right.
say in the visit class, we are going to add to see whether we need this.
Right.
Right?
But when you get to the end, even once it sees every vertex, it'll just go through all the unnecessary edges.
All the unnecessary ones. Yeah. I mean, it just throw them away. That's the throwing away step is the continue step part of it.
Yeah.
Right? The continue is the one that's throwing the unwanted edge away. So it's a slightly modified version of it, but it's again, the Boolean acts like the union find thing. It's a fairly flat union find. What about the cost of it?
Of the union find, or just in general?
And the maximum cost of it in general. So we want to identify. So if we want to identify the worst offending cost.
It would be equal to the number of vertices, right?
So the heap is the cost, right? And on the worst case, it's the heap. The only place where we are creating a cost is creating the heap. moving from the heap, and right. The other is, so here there's a heap cost, right? So this is removing from the heap. This is adding to the heap. No, it's not this one. That's not the one. The cost. The cost is here. Priority queue dot insert. That's right. You see where the cost is. This is the costly operation. That's the heap. We are adding the edge into a heap. And heap is a log thing. Heap is like a binary tree, right? Nicely balanced binary tree with the swim and the sync operations attached to it. So how do we insert? When we are inserting, we add it to the end and then swim that up. Right? So whichever edge we add it as the last entry on the heap and then swim that. You remember how to insert into a heap? And that's what the heap operation is. Right? And then, of course, how do we remove from a heap? What's the process for removing from the heap?
You remove the top and then
remove the top and then what do we do?
We put something from the bottom at the top and then sink it down.
Yeah, you swim up.
Sink down. Remove the last guy from the heap and then sink it down. Right? So you're going to remove the remove from the top, remove the CEO from the company. And then who is the last person in that company? Take it, put it on the top of the heap, and then sink that thing down so that it gets to where it needs to be. And what is the process of sinking? Is promote the most qualified person to the position. Look at the two children of the node, and whichever that happens to be the one that's most qualified, move it up and then sink the one down and repeatedly do that. And on the worst case, we may have to do this E times. Right? So E log VE is the cost. The cost is E. So there are E, right? We have a list of E edges. The cost of creating a heap is log E. And the number of times we'll have to repeat that is E. Because we may have to go through and list, because the heap consists of all the edges, and the worst case is E log E. So the cost of the minimum spanning tree using Prim's algorithm is E log E. Okay. So we need to kind of know how these algorithms work. Like the one algorithm I gave you in the exam, I thought I gave you those are the easiest ones. The ones which had the least number of lines to write. Right? I mean, swim and sink are like, really, it's an array-based algorithm. It's only 3 lines of code. Right? I mean, if you look at the code in the book, it's only 3 or 4 lines at most. And then, of course, the binary tree, we kind of need to know how the binary tree works. You scan for left or right. Right? So this is one of those easy algorithms to remember. Just if you understand how it works, that right. So this is one of the algorithms. How does Kruskal's algorithm work? What's the principles with Kruskal's algorithm?
You organize edges in order of descending weight?
Yes, right? So you can create a heap again, right? Create a heap with all the edges in it. So previously we were creating a heap with only the crossing edges in it. This time we are going to create a heap with all the edges in it. Right? So we have a heap with all the edges, and then all we have to do is, let's see which ones we want to remove. As we are removing things, we are going to say, okay, let's take the one that's a minimum. Now, do verify whether this edge is needed or not, meaning 0 and 7 are in two different cuts. Right? If 0 and 7 are in two different cuts, then do we need it? So what we are doing this time is we are going to start with, like the union find, we are going to start with lots of cuts, like all these things in different cuts. Like what union find did. We put all of them in two different cuts, or all of them in cuts. And let's take the first edge and see, okay, 0 and 7, are they in two different cuts? Initially, yes, they are in two different cuts, right? Because 0 is in its own cut, because every vertex is in a separate set. Because they're in two different cuts, we need that, because that's going to be a cut anyway. This is 0 against everyone else. That's 0 against everyone else, or 7 against every other node. So we will need that edge. That's going to be a minimum cut. That's a cut. That's a minimum cost cut. Right? So we take that edge. Okay, we have done that. 2 to 3. 2 to 3, are they in two separate cuts? Separate set? Yes. So that means we'll need that too. Unlike prims that grows from a given, it kind of grows from a vertex, this is randomly growing all over the place. It's randomly choosing the edges and says, okay, these two are in two separate cuts, therefore I'll need them.
So won't you have to keep track of a bunch of different sets?
Yes, right? But the bunch of different sets, and that's where the union find would be really helpful. Because that's what union find is, right? A bunch of different sets, and then we identify which two nodes belong to the same set, or if they don't belong to the same set. So then we take 2 to 3, we need it. 1 to 7 are still in two different sets, so therefore we'll need that too. So so if you mark the ones we need the first 3. Need that one, we need this, we need that. 0 to 2. They'll be in two different cuts, because 0 and so now if you look at this, 0, 1, 7 is in one set, because now we have done a union find to make that one set, and then 2 and 3 are in another set. And then the other vertices 4, 5 and 6 are in their own sets. 4, 5 and 6 are in their own sets. 0 to 2, yes, we need them. So that means that these two now get combined into one set now. The union command will do that for us. 5 to 7, we need that too. And we need 5 to 7. So now we have a set that consists of all the 3 different sets now. 4 different. So 2, 3 is connected. 5 is also now connected to the same set now. 1 to 3. Do we need 1 to 3? What did I do? Did I do something wrong? I did 0 to 2. That means I did this one. Right? So I wanted 0 to 2. So what about 1 to 3? Do I need 1 to 3?
No, you don't.
We don't. So we throw that away. 1 to 5. We don't need that. 2 to 7. We don't need that. And then 4 to 5. We don't need that. 1 to 2. We don't need that. 4 to 7. No. 0 to 4. Then the next one is 6 to 2. And then the others you don't need. 3 to 6. 6 to 6. We don't need this. Right? So slight variation, but it's very similar. I mean, the principle is based on the fact that the minimum spanning tree will include the edge with the minimum cost in any crossing cuts. It was just a matter of how we go about selecting the edges. Other than that, nothing has changed. Right? So if you grow it like that, the rest of the slides actually kind of show you how this thing, where's my mouse? It's on this side. It grows like that. Right. How do you think? So any questions on the process of how it's done?
No, that's good.
Right? So let's go and look at the code and see how the code looks like. And that one. Right. So there's a couple of challenges here. So there is one thing we need to check here is, would adding a edge from V to W to the tree minimum spanning tree create a cycle or not? If it doesn't, add it. And the way to find out whether it will create a cycle is that we probably should use a union find algorithm to do that. And if you use a union find, that will tell us whether you're going to add an edge that's going to create a cycle, because that will identify whether both ends of the edge is in the same cut or not. So we need that. Right? And then we need a priority queue to be able to do that. So that's what we are going to do. Kruskal's algorithm, we start off by creating a queue that's going to include all the edges in the minimum spanning tree. Step number 1, what's this one for?
That makes our priority queue.
Of all the edges, right?
Edges, right.
Yes, right. Make a priority queue for all the edges. Now, you also need a union find. A union find that puts all the vertices in their own sets. Right? So all the vertices end up being in its own set. And then we repeat. Right? So this one we can stop early. Meaning that, okay, do we have to go through all the list? Probably not. My two conditions are, while the priority queue is not empty, that I have not processed all the edges yet. And if I process all the edges, I can stop. There's nothing to process anymore. The other condition here is this one. This is where I'm saying the minimum spanning tree, the number of edges that's in the minimum spanning tree is less than v minus 1. So I count the number of edges to see how many edges have I included. And the number of edges in the minimum spanning tree is, if there's v, it's v minus 1. And if there are 2 edges, it's 1. If there are 3 edges, it will be 2. Or 3. If there are 2 vertices, the number of edges is 1. If there are 3 vertices, the number of edges will be 2, like that. So I count the number of edges to see, okay, should I keep going through the rest of the priority heap or should I stop now? If both conditions are met, then delete, remove the edge with the minimum cost, find out the 2 vertices that's connected to the edge, newly removed edge, see if they are connected or not. Do a union find to see whether they are connected. If they are not connected, connect them, do a union operation, and then enqueue the vertex or the edge, enqueue the edge. So that means that's added to the minimum spanning tree. Repeat this process again and again and again until done. Right? So these are the 2 implementations of it. Frames and Kruskal's algorithm. Extremely easy once we know what a crossing cut is.
Is one better than the other?
Well,
like
what's
time
the
efficiency?
So what's the cost of it, right? What's the cost of Kruskal's? It's right. So the cost is going to be, there are 2 places where we have a cost. So building the priority queue, we need to add all the edges into that. Deleting the minimum is a cost log E. So we have to create the priority queue once. Right? And then we need to delete the number of edges to be deleted. We have to delete it E times. Right? And then union is we may have to do, union is going to be V times log V, and connected, we have to check that E times log V. So the cost is, if the edges are already sorted, then the cost is E log V. If not, this one. Where does this come from?
I mean, that's the heap. Right?
That's the build. Yeah, that's building the first heap. That's building the first heap. So E log E is the worst case cost. And what did we find for over there? It's very similar in terms of cost. Right? It's E log E both cases. Right? If you're starting with an unsorted list of edges, then it doesn't matter which one we use. If the edges are already sorted, then we can go with Kruskal's, because then we can use, the only cost is the union find algorithm, and union find we can make it very fast. We can use weighted union, we can use compressed path union, all the different ways of doing a union find. That will make it a little shorter. So that's the quick union find. Any questions before we stop? No? And were you able to read the eCollege page? I believe that there was a problem with the eCollege like on Monday and Saturday, Sunday, Monday. So now you should be able to see working end of Monday.
Yeah, it started working for me.
Yeah, right. So check all the assignments have been posted, so please submit them soon. I mean, if you do it today, you'll remember it. If it's so easy that you leave it for a week or two, then you say, "Oh, what did I do?" I mean, these are not difficult things. If you do it right away, that's where things get delayed. Only because you postpone it. It's this tortoise and the hare type of thing. It's easy. Let me sleep and then come back and wake up and do it. Right? Instead, just do it right away. You'll be done. So there's an assignment on Kosaraju's connected components, depth first search, pre-order traversals. And there are two programming assignments. One is on minimum spanning tree and the other is on shortest path. And we'll discuss that next time and see how it's done. Okay? But before you start on the programming, at least do the handwritten ones.
All right.
Okay, I'll see you Monday then.
Okay,
Thank you.
See you. Thanks so much.
Yep.